Imagine waking up one day only to find that reality itself is glitching. The ground beneath you flickers, the sky warps in unnatural patterns, and time itself seems to loop and fracture. No, this isn't science fiction. It's the terrifying possibility lurking within the bizarre rules of quantum mechanics. From quantum fluctuations that could rewrite the fabric of space, to vacuum decay that could obliterate the universe in an instant, the smallest particles in existence may hold the key to our ultimate doom. And worse, some of these catastrophic events might already be in motion. Welcome to the unsettling world of quantum quakes, where the tiniest forces in nature might just tear reality apart. Foundations of quantum reality, the birth of the quantum revolution. In a world where the unchangeable rules of classical physics were believed to govern all events, it would be easy to see the cosmos as a clockwork mechanism. Newton, Maxwell, and all that followed them had this cozy worldview. For a long time, people thought the universe was a gigantic machine whose movements could be anticipated given the locations and speeds of all objects. The deterministic picture was shattered at the turn of the 20th century by a string of groundbreaking discoveries that gave rise to quantum mechanics. This theory did more than just reframe our perception of the microscopic world. It also provided the groundwork for the mind-bending scenarios depicted in the script. The revolution began with Max Planck's introduction of the quantum hypothesis in 1900. Faced with the problem of black-body radiation, where classical theories predicted an infinite amount of energy at short wavelengths, Planck proposed that energy is not continuous, but instead comes in discrete quanta. This bold idea, initially a mathematical trick, suggested that energy could be emitted or absorbed only in fixed amounts, a concept that would soon prove to be profoundly true. Planck's constant, a tiny number that emerged from his work, became one of the cornerstones of quantum theory, symbolizing the granularity underlying the fabric of reality. Albert Einstein furthered these ideas in 1905 with his explanation of the photoelectric effect. By proposing that light itself is made up of individual particles, later called photons, Einstein provided compelling evidence that energy transfer occurs in discrete chunks. His work not only confirmed Planck's hypothesis, but also hinted at the dual nature of light, a particle and a wave simultaneously. This duality was later extended to all matter, laying the groundwork for the concept of wave-particle duality, which remains one of the most startling revelations of quantum mechanics. Niels Bohr built on these discoveries with his model of the hydrogen atom, introducing the notion that electrons orbit the nucleus in specific quantized energy levels. According to Bohr, electrons could jump between these levels by absorbing or emitting energy in precise amounts. Although his model was later refined, it captured the essence of quantization and demonstrated that even the atoms, the very building blocks of matter, were subject to discrete, probabilistic rules rather than continuous, deterministic motions. The theoretical framework of quantum mechanics was further refined by the work of Louis de Broglie, who in the 1920s proposed that particles, such as electrons, possess an intrinsic wavelength. This idea led to the development of the Schrödinger equation, a fundamental equation that describes how the quantum state, or wave function, of a system evolves over time. Erwin Schrödinger's formulation replaced the rigid orbits of Bohr's model with a probabilistic cloud, where the position and momentum of particles were given in terms of probabilities rather than certainties. Werner Heisenberg's uncertainty principle, formulated around the same time, further deepened the mystery. It revealed that certain pairs of physical properties, such as position and momentum, cannot both be known to arbitrary precision simultaneously. This principle shattered the classical notion of an entirely predictable universe, suggesting that at the very heart of matter lies an intrinsic uncertainty, a fundamental fuzziness that defies the precision of classical measurements. The work of these pioneers not only redefined the microscopic world, but also posed deep philosophical questions. If particles do not have definite positions or speeds until they are observed, then what does it mean for something to exist independently of observation? The idea that reality is not fixed until measured challenged centuries of philosophical thought and raised questions about the nature of consciousness, observation, and the very fabric of reality. Experiments started to confirm quantum mechanics' contradictory predictions as the theory developed. Example: the well-known double-slit experiment demonstrated that photons and electrons behave like waves in their interference patterns, yet look as separate particles to the naked eye. A recurrent topic in our study of quantum cataclysms is the centrality of measurement to the behavior of quantum systems, as demonstrated by these experiments. As a result of quantum mechanics' theoretical foundations, contemporary quantum field theory was able to describe how particles arise from space-permeating underlying fields. From this perspective, the vacuum is far from empty. Rather, it is a boiling pot of changing fields in which particles and antiparticles continually enter and exit the body. Even nothingness contains shape and energy, according to this vivid depiction of the vacuum, which is crucial when talking about quantum fluctuations and vacuum decay, among other things. The creation of quantum physics was not just a big change in science, but also changed how we view the world. It replaced the certainty of classical physics with a probabilistic universe, a realm where chance, uncertainty, and the act of observation determine the course of events. This new viewpoint has significant effects, forming the foundation for the amazing tools we have today and the possible disasters we will discuss later in this text. Quantum catastrophes through history, from theoretical curiosity to cosmic threat. Early talks about vacuum changes and the quantum vacuum led to fears and concerns about potential disasters. When scientists studied quantum field theory, they discovered that the void is not really empty. Instead, it was an active and changing space where particles and antiparticles appeared and destroyed each other in a constant movement. This image of a busy vacuum sparked early discussions about whether these changes could, in rare situations, combine to create important cosmic events that might change our understanding of physics. Pioneers like John Wheeler and Richard Feynman were among those who pondered the profound implications of a restless quantum vacuum. Wheeler's concept of quantum foam painted a picture of space-time so turbulent at the smallest scales that its smooth appearance in our everyday experience was merely an emergent property of averaging over countless fluctuations. This foam, he suggested, might harbor instabilities that, if amplified, could lead to catastrophic phenomena such as vacuum decay, a process where a tiny fluctuation triggers a chain reaction that changes the fundamental state of the universe. As theoretical research progressed, the idea of vacuum metastability emerged. The possibility that our universe might exist in a metastable false vacuum, a state that appears stable but is not the absolute lowest energy configuration, captured the attention of many scientists. Early discussions speculated that a rare quantum tunneling event could cause a bubble of true vacuum to nucleate and expand at the speed of light, ultimately consuming the universe in a cataclysmic phase transition. Though such ideas were considered highly unlikely on human timescales, they challenged the notion of eternal stability and hinted at a dark fate that might await our cosmos billions of years from now. Not all of these early talks were just interesting ideas. Experimental results like the Casmir effect supported the idea that empty space has energy and a certain structure. These tests showed that even empty space has strange qualities that go against our usual understanding, suggesting that the quantum world might have risks we can't fully grasp. By the 1970s and 1980s, with the development of grand unified theories, GUTS, and the subsequent refinement of quantum field theories, the specter of quantum catastrophes became a recurring theme in high-energy physics. Many researchers began to ask whether the fundamental forces of nature, unified at high energies, could hide latent instabilities that might one day be unleashed. The possibility of proton decay, a process predicted by many GUTS, was not only a key to unifying forces, but also a stark reminder that even the building blocks of matter might not be eternal. These early ideas about quantum catastrophes were not limited to universities. They started to influence popular culture, inspiring science fiction writers and directors to create stories about worlds where reality could suddenly break apart. This interest in culture raised people's understanding of the important effects of quantum physics, mixing ideas from imagination and actual science. As the field advanced, the discourse evolved from abstract musings to detailed analyses of how quantum effects could manifest on a macroscopic, even cosmic scale. Researchers started to consider scenarios where quantum tunneling might lead not only to nuclear fusion in stars, but also to potentially dangerous chain reactions, processes that, if triggered under the wrong conditions, could have catastrophic consequences for the universe. Quantum fluctuations, the universe's endless jitter. Quantum fluctuations are essential to our current understanding of the basic structure of the world. Even though many people think of empty space as empty, quantum theory shows us that it's actually a lively place where the basic nature of reality is always changing and full of action. In quantum field theory, every point in space is filled with fields like the electromagnetic field and the Higgs field. Each of these fields has its own natural energy that causes them to vibrate. This restless energy is not just a theory, it is something we can actually measure. For example, in the Casmir effect, two uncharged plates put parallel to each other in a vacuum pull toward each other because of uneven quantum changes between them. Quantum fluctuations happen because of the uncertainty principle created by Werner Heisenberg. The uncertainty principle states that you cannot measure certain sets of physical properties, like energy and time, exactly at the same time. This basic limit means that, for very short periods, a system's energy can briefly change from its usual level. These brief energy changes create virtual particles, short-lived particles that appear from nowhere and disappear quickly. In this tiny interaction, particles and their opposites appear quickly from energy and then almost immediately destroy each other. Even though we can't see virtual particles directly, they have important effects that we can measure. These effects help us understand the workings of the quantum world better. Picture a calm lake that looks completely still at first. However, upon closer inspection, you observe that the surface is punctuated by countless ripples and eddies, a subtle but perpetual motion that belies the lake's placid appearance. This is similar to a quantum vacuum, where what seems like empty space is always moving and busy. These changes aren't random. They follow the rules of quantum mechanics and reflect the basic fields that shape the world. Every small change reminds us that empty space is full of energy and is constantly shaping the story of the universe. The implications of quantum fluctuations extend far beyond the realm of theoretical musings. They are believed to play a crucial role in the early universe, influencing the formation of galaxies and large-scale cosmic structures. In the moments following the Big Bang, the quantum jitter of the vacuum may have seeded tiny density variations, which, over billions of years, grew under the force of gravity into the vast cosmic web we observe today. Thus, the very patterns that define the large-scale structure of the universe owe their origin to the subtle and relentless motion of quantum fluctuations. There is also a more worrying option in this constant movement. Everyday quantum fluctuations are harmless and important for the development of the world, but they also suggest the possibility of more dramatic events happening. In specific situations, a quantum fluctuation could, in theory, become stronger and last longer than usual. If this kind of increase happens in empty space, it could cause a change in space-time, which could then lead to a chain reaction that changes the basic rules and forces of the universe. This hypothetical situation is a key part of talks about vacuum decay and how stable our universe is. In this situation, the randomness of quantum changes is not just a simple interest. It has both positive and negative effects. These changes create the variety in the world, leading to the formation of matter, energy, and structure. However, they have an inherent instability, showing that the quantum world is always changing and can affect the balance of the universe. The same chances that help form stars and galaxies also mean that a small change could potentially trigger a harmful chain reaction, even if it's unlikely. When we think about the active energy in the quantum vacuum, we realize that our world is not calm at all. Instead, it is an active and lively space where even tiny changes can spread out and affect the entire universe. The constant movement of the vacuum represents a puzzle in quantum mechanics. This area is full of endless possibilities, but also has a basic unpredictability that, in certain situations, could change the fundamental rules of physics. Vacuum decay, when nothingness destroys everything. Vacuum decay is a surprising and concerning thought from quantum field theory. It suggests that empty space, which we usually see as harmless, could actually lead to a major cosmic disaster. This idea suggests that what we think of as a vacuum isn't really completely empty. Instead, it has a certain energy level. In quantum field theory, every field, like the electromagnetic field or the Higgs field, has a vacuum state, which is the lowest energy state the field can be in. This state might not be the lowest energy state possible. It could be a false vacuum. This means that it looks stable, but is actually above the true vacuum, which is the lowest energy state. Imagine a ball resting in a narrow valley, when, invisible to its spectator, a deeper valley lies just beyond a nearby hill. Under this comparison, the present vacuum state of our universe is like the ball in the shallow valley, a condition that seems steady but is not the most energetically beneficial. Quantum mechanics indicates that, although small, there is always a chance the ball will tunnel across the hill and roll down into the deeper valley. Within the framework of vacuum decay, this tunneling marks a quantum event whereby a small area of space moves from the false vacuum to the actual vacuum state. This transition doesn't occur gradually or quietly. It initiates a dramatic process. When a region of space undergoes vacuum decay, it forms a bubble of true vacuum. This bubble is not a mere void. It is a region where the fundamental properties of space, including the forces and particles we observe, are entirely redefined. The bubble, once nucleated, is predicted to expand at the speed of light, consuming everything in its path and replacing the false vacuum with the new, lower energy state. In effect, the entire fabric of space-time would be rewritten, with the laws of physics as we know them altered beyond recognition. Galaxies, stars, planets, and even the atoms in your body would be subsumed into this radically different state, rendering our universe unrecognizable or obliterated altogether. The intrinsic unpredictability of vacuum decay is one of its most fascinating features. Given the probabilistic nature of quantum physics, the chances of a tunneling event happening in a specific region of space within a certain time frame are extremely low, but not zero. In theory, a quantum fluctuation anywhere in the universe may set off vacuum decay. Because quantum mechanics is inherently random, our universe could still collapse at some point, even if it has been in a metastable state for billions of years. This could be due to a small nucleation event that builds into a bubble of disaster. The implications of vacuum decay are as profound as they are terrifying. To grasp the full impact, consider the effect on fundamental forces. In a false vacuum, the constants that govern interactions, such as the strength of the electromagnetic force or the mass of elementary particles, are finely tuned to create the universe we experience. A transition to the true vacuum could, in theory, alter these constants instantaneously. This means that the chemical bonds holding matter together, the forces that drive nuclear reactions, and even the geometry of space-time itself could change. The resulting environment would be incompatible with the structures that define our current reality. Stars might no longer burn, planets could disintegrate, and life, as we know it, would cease to exist. Even though vacuum decay has serious implications, most scientists believe that the false vacuum in our universe is very stable and will last a long time. Recent experiments about the Higgs boson and the stability of the Higgs field show that our vacuum is likely not completely stable. However, the chance of it changing in a way that affects us is extremely low, possibly taking much longer than the age of the universe itself. Even the unlikely chance reminds us that we don't fully understand the universe. The world works in ways that are often surprising and different from what we expect. Vacuum decay is a clear example of how quantum mechanics can shake up our beliefs about how stable and lasting things are. Moreover, the concept of vacuum decay stretches beyond pure academic speculation. It has profound implications for cosmology and the ultimate fate of the universe. If our vacuum were to decay, the ensuing bubble would expand relentlessly, its boundary moving outward at light speed. The transition would be sudden and total. There would be no gradual warning, no slow shift in the properties of matter. Instead, the true vacuum would simply supplant the false vacuum everywhere it reached, a cascade of change that would transform the cosmos in an instant. The idea that an event as seemingly insignificant as a quantum fluctuation could precipitate such dramatic consequences underscores the inherent unpredictability of the quantum realm. Discussions of vacuum degradation also lead to profound philosophical inquiries into the essence of reality. Since even vacuums are transient, how can we say that the cosmos is stable? How can we make sense of quantum theory's suggestion of fundamental fragility in light of our experience of a robust world? Every solution to these questions unveils more levels of intricacy and mystery, reminding us that our comprehension of existence is fundamentally a work in progress. False vacuum collapse, a bubble of doom. A false vacuum collapse is an interesting and frightening idea. It shows how the fragile balance of quantum states could someday cause a huge response that changes reality itself. Right now, we see space as not completely empty, but as a state that has energy. The space we live in might not be the most stable form it can be. Instead, it could be a false vacuum, which seems stable most of the time, but has the possibility for sudden change. Think of our universe like a land with hills and rivers. The false vacuum is like a shallow valley where the universe seems comfortable. But hidden beyond a nearby ridge lies a deeper valley, a true vacuum, representing a lower energy state. The false vacuum can last for a very long time, but quantum physics shows that there is always a small chance for a part of space to switch to a lower energy state. When this change happens, it creates an area of true vacuum, where the basic rules of physics are very different from what we understand. This bubble of doom would not expand gradually, rather, it would grow at the speed of light, racing outward and consuming everything in its path. As it spreads, the bubble redefines the very constants and interactions that govern the forces of nature. The electromagnetic force, the strong and weak nuclear forces, even gravity could be altered as the new vacuum takes hold. What might seem like a minor shift in the energy landscape at the quantum level could thus unleash a transformation of cosmic proportions. Every particle, every star, and every galaxy would be swept into this new state, leaving behind a universe with entirely different physical laws. A reality where the familiar structures that support life and matter may no longer exist. The mechanism behind this collapse is rooted in quantum tunneling, a process that allows particles, or in this case, regions of space, to transition between states without overcoming an energy barrier in the classical sense. In our false vacuum, the energy barrier separating it from the true vacuum is finite but significant. Nonetheless, quantum theory predicts that given enough time, even such a barrier can be breached. The probability of this happening may be extremely low, but on cosmic timescales, extremely low does not equate to impossible. Even if the odds are minuscule, the mere possibility that a bubble of true vacuum could nucleate anywhere in the universe sends shivers down the spine of theoretical physics. Once initiated, the collapse would be both swift and irrevocable. The bubble's boundary, or domain wall, would act as a front line between the two competing vacua. As it expands, it converts regions of false vacuum into the new state with radically different properties. This conversion would be accompanied by violent releases of energy, as the rearrangement of the vacuum structure disrupts the equilibrium of forces that currently hold matter together. In effect, the universe's operating system would be forcefully overwritten, erasing the old code and replacing it with a new, unpredictable one. This phenomenon is not merely a speculative exercise in theoretical physics. It has deep implications for our understanding of cosmic evolution. If our universe is indeed in a false vacuum state, then the stability we observe is only temporary. Although current measurements, particularly those related to the Higgs boson and the behavior of the Higgs field, suggest that our vacuum might be long-lived on timescales that far exceed the current age of the universe, the inherent uncertainty of quantum processes means that a catastrophic collapse cannot be entirely ruled out. This possibility serves as a humbling reminder of the inherent limitations of our scientific models and the unpredictable nature of quantum phenomena. The effects of a false vacuum fall go beyond just space science. It makes us rethink what we believe about how permanent and stable things are in the world. We often see physical rules and constants as unchanging foundations of reality. The idea that these laws could change dramatically suggests that our understanding of the world is not final and depends on a balance that could shift in unexpected ways. A false vacuum fall reminds us how fragile and temporary life is. As a science where even the tiniest changes can have far-reaching effects, quantum mechanics embodies this duality in the picture of a bubble of disaster. There is a possibility that a universal reset may be initiated via the same quantum tunneling technique that might enable particles to flow past barriers in a controlled environment. The interaction between order and disorder, creation and destruction, both controlled by the same set of probabilistic laws, is central to many contemporary physics topics. Quantum tunneling, particles cheating reality. Quantum tunneling is a process that goes against what we expect based on classical physics and shows a major difference between the tiny world of quantum physics and the larger everyday world. In classical physics, particles are stuck by barriers because they don't have enough energy to get past objects that are taller than their movement energy. However, quantum physics takes a completely different approach to this idea. According to quantum theory, particles don't follow specific paths. Instead, they are represented by wave functions, which show the likelihood of where they might be. This wave-like behavior means that there's always a chance for a particle to be found beyond an energy barrier, even if it doesn't have enough energy to cross it in the usual sense. To understand quantum tunneling, imagine a ball rolling toward a hill. In a classical scenario, if the ball lacks sufficient energy, it will roll back down the hill. Yet, in the quantum realm, the ball has a chance, no matter how small, to appear on the far side of the hill, as if it had tunneled through it. This counterintuitive behavior is not merely a mathematical curiosity. It has been observed and measured in countless experiments. For instance, tunneling is the key mechanism behind nuclear fusion in stars, where protons overcome their electrostatic repulsion and merge to release vast amounts of energy. Without tunneling, the process powering our Sun and other stars would be impossible. Quantum tunneling has effects that go beyond just the innards of stars. In today's technology, tunneling helps make devices like the tunnel diode and the scanning tunneling microscope work. The scanning tunneling microscope lets scientists take pictures of surfaces at the atomic level. These examples show that tunneling is a dependable and known process in its typical situation. But when we apply this idea to more unusual situations, the risks become much greater. Consider the possibility that quantum tunneling could facilitate events on a macroscopic or even cosmic scale. In the controlled environment of a laboratory or within the core of a star, tunneling is a benign process governed by well-established probabilities. But what if, under extreme conditions, tunneling were to occur in a way that triggers a catastrophic chain reaction? Some speculative theories suggest that if a critical particle were to tunnel through a barrier in a highly unstable environment, such as within the Earth's core or in the fabric of space-time itself, it might initiate a domino effect leading to runaway reactions. One such scenario is the hypothetical ignition of Earth's core, where a single aberrant tunneling event could theoretically set off a chain reaction of energy release, altering the planet's internal dynamics with disastrous consequences. Another important option includes how tunneling works together with other quantum processes. In places like particle accelerators, particles are speeded up to almost the speed of light and then impact with each other. In these crashes, the very intense conditions can briefly allow particles to reach energy levels where the usual rules don't work as expected. There is a possibility that tunneling events could occur, which might ignore normal physical limits. This raises worries about unexpected chain reactions, but current studies and safety measures indicate that these concerns are mostly just ideas and not likely to happen. Micro-black holes, accidental creation and catastrophe. Micro-black holes are an exciting and uncertain area where quantum physics and general relativity meet. In theory, in very high-energy places like the Large Hadron Collider, particles can crash into each other with enough energy to quickly form tiny black holes. These are not large black holes created from falling stars. Instead, they are tiny changes in spacetime that could be smaller than an atom. Some quantum gravity models suggest that extra dimensions might make gravity much stronger over short distances. The main idea is that spacetime is made up of tiny bits when looked at with very high energy. These models suggest that when particles collide at speeds close to the speed of light, the energy in a small area can briefly become high enough to create a tiny black hole. Most theories suggest that these tiny black holes will quickly disappear due to Hawking radiation, which is when black holes lose mass by releasing particles. This process is expected to happen so quickly that any black hole formed in a particle collider would vanish before it could affect anything around it. However, the scenario becomes much more unsettling if the expected evaporation fails to occur. If, contrary to our current understanding, micro-black holes were stable or had a much longer lifetime, they could, in theory, begin to accumulate matter. Imagine a tiny black hole lingering within the dense environment of a particle accelerator, or more alarmingly, within the Earth itself. Over time, such a black hole might begin to absorb the particles around it, growing ever so slightly with each passing moment. Although the rate of accretion would likely be exceedingly slow at first, the fundamental properties of black holes suggest that even a minuscule object with an intense gravitational field could, if given enough time, lead to runaway growth. This possibility, while highly speculative, has been the subject of intense debate among physicists. Extensive safety reviews have been conducted regarding high-energy particle collision experiments, and current consensus holds that the conditions necessary for creating dangerous micro-black holes are either unattainable or that any black holes produced would decay too quickly to pose a risk. Nonetheless, the theoretical framework that allows for their creation remains a vivid illustration of how quantum effects might have macroscopic and potentially catastrophic consequences. Also, the idea of micro-black holes raises important questions about how the cosmos is built. It requires us to bring together quantum mechanics and Einstein's theory of relativity, two important parts of modern physics that, although they have been successful, are not completely joined together yet. In this discussion, we consider that our small-scale studies might accidentally explore events that could significantly affect spacetime. Although the chance of a micro-black hole becoming something important in space is very small, talking about it highlights an important idea in modern physics. Even small quantum events can lead to surprising and sometimes dangerous results. Hawking radiation's failure when black holes don't die. Stephen Hawking's groundbreaking prediction that black holes emit radiation, a phenomenon now known as Hawking radiation, has reshaped our understanding of these enigmatic objects. According to his theory, quantum effects near a black hole's event horizon cause it to lose mass by emitting particles over time. In essence, particle-antiparticle pairs emerge from the quantum vacuum near the edge of the black hole. One particle falls in while the other escapes, effectively reducing the black hole's mass. Over vast astronomical timescales, this process leads to the gradual evaporation and eventual disappearance of the black hole. Yet, What if this elegant mechanism does not operate as expected? The possible failure of Hawking radiation adds an unsettling element to our theories. If tiny black holes, which are small changes in spacetime formed under extreme conditions, do not disappear as expected, they could last much longer than we think. These tiny black holes might not disappear quickly. Instead, they could stick around and gradually gain mass by pulling in nearby particles. Even if the accretion process is extraordinarily gradual, the idea that these objects might not vanish as predicted challenges our safety assumptions. In places like particle reactors, where small black holes might form, it is believed that they would quickly disappear. This idea is important for calming fears about any serious dangers. If this behavior changes, a harmless quantum process could become a danger. The main issue is that we don't fully understand quantum gravity yet. Hawking radiation is drawn from a semi-classical approach, an approximation that merges quantum mechanics with general relativity, but it may not capture the full complexity of a complete quantum theory of gravity. There might be some unknown reasons or changes in the theory that could reduce the release of radiation, but this is just a guess. If the melting process is not as effective as expected, even a tiny black hole created in a controlled experiment could last long enough to start affecting its surroundings more. Over time, this could cause unexpected chain reactions, as the black hole's gravity slowly changes the arrangement of nearby matter. The failure of Hawking radiation would compel physicists to revisit and refine our theoretical frameworks. It would serve as a stark reminder that even our most celebrated predictions remain provisional in the face of the universe's intricacies. The notion that a micro-black hole might not die as expected underscores both the promise and the peril inherent in probing the quantum frontier. Large Hadron Collider experiments, playing with cosmic fire. In high-energy physics, few tests are as impressive and nerve-wracking as those done at the Large Hadron Collider, LHC. Situated at the forefront of scientific discovery, the LHC accelerates particles to near-light speeds and collides them, recreating conditions similar to those in the early universe. This major effort has resulted in important discoveries, especially the finding of the Higgs boson, which has enhanced our knowledge of the basic components of matter. However, the very high energies used in these experiments have led to discussions about the possibility of causing events that could affect the basic nature of our world. By smashing particles together at unprecedented energies, the LHC might inadvertently create exotic forms of matter or even trigger a catastrophic event. Among the theoretical scenarios is the production of micro-black holes, a subject we have explored earlier, where the intense energy density could, in theory, warp spacetime on an incredibly small scale. While the prevailing consensus is that any micro-black holes generated would evaporate almost instantaneously via Hawking radiation. The sheer magnitude of energy involved leaves room for imaginative, if highly improbable, possibilities. Some have speculated whether these high-energy collisions could destabilize the vacuum or even give rise to strange matter, a hypothetical form of quark matter that might convert ordinary matter into an exotic, unrecognizable state. The LHC pushes the boundaries of our current theoretical frameworks by probing energy regimes where the familiar rules of physics begin to blur. At these scales, even minute deviations from expected behavior could, in theory, cascade into unforeseen phenomena. The possibility that a single high-energy collision might trigger a chain reaction, such as a localized vacuum decay or the onset of exotic matter formation, has been raised in speculative discussions. Though rigorous safety protocols and extensive peer review have consistently affirmed that such risks are astronomically low, the mere discussion of these possibilities underscores the precarious balance between scientific advancement and cosmic safety. The experiments at the LHC also serve as a humbling reminder of our incomplete knowledge of the universe. Every clash is carefully studied to support or question our particle physics models. Each step into high-energy experiments brings us closer to discovering new things. the LHC has a reputation for mixing careful experiments with the exciting chance of discovering surprising things. This is why it is often called a modern Prometheus, like taking fire from the universe, which comes with its own risks. Strange matter, the ultimate chain reaction. Strange matter represents one of the most intriguing and possibly catastrophic hypothetical forms of matter in the universe. Strange matter is a kind of quark matter that is believed to have an equal mix of up, down, and strange quarks. Unlike protons and neutrons, which are made of just up and down quarks, strange matter includes a new type of quark called the strange quark. In extreme situations, like in the center of neutron stars, matter can get so dense that it changes into a more stable form. The surprising idea is that if a small piece of strange matter, called a strangelet, touches regular matter, it could change that matter into more strange matter, causing a chain reaction. A small weird matter nucleus can be created through a very unusual quantum fluctuation, or as a result of very energetic collisions. As soon as it takes shape, this oddlet may start communicating with surrounding atomic nuclei. As usual, stuff is transformed into weird matter. The process is thought to be exothermic, which means it could release more energy. The process would run itself, producing additional strangelets with the ability to convert more material with each conversion. Planets, stars, or even entire parts of the universe could be transformed into a uniform state of unusual matter if a single spark ignites a wildfire that persistently spreads in a massive pile of ordinary matter. The theoretical underpinning for such a cataclysmic chain reaction stems from the idea that strange matter might be energetically more favorable than normal nuclear matter under certain conditions. If this is indeed the case, then the conversion process would be spontaneous, driven by the search for a lower energy configuration. It is important to note that this is a speculative scenario, while experimental searches have yet to uncover evidence of strangelets or runaway conversion events. The mere possibility remains a topic of discussion among theoretical physicists. The dangers associated with strange matter are not merely confined to the realm of science fiction. They highlight a fundamental question in high-energy physics and cosmology. Could our experimental forays into extreme states of matter inadvertently trigger a chain reaction with universal consequences? Particle accelerator experiments, such as those conducted at the Large Hadron Collider, have occasionally raised concerns that the high-energy collisions might produce strangelets. However, extensive theoretical work and observational data from cosmic rays suggest that, if strange matter exists, the conditions required to initiate such a reaction are unlikely to be met in any terrestrial experiment. Cosmic rays, nature's particle accelerators, gone rogue. Cosmic rays are high-energy particles that constantly bombard Earth from outer space, acting as nature's own particle accelerators. These particles, which include protons, electrons, and atomic nuclei, travel across vast interstellar distances at nearly the speed of light. Their origins are varied, stemming from supernovae, active galactic nuclei, and other energetic cosmic events, and they carry energies far exceeding those produced by human-made accelerators. In many respects, cosmic rays are a window into the most extreme processes in the universe, offering insights into the behavior of matter and energy under conditions that are impossible to replicate on Earth. Normally, cosmic rays are harmless and can help create things like auroras and some chemical processes in the atmosphere. The features that make them useful for studying space also suggest they could have a negative side. At very high energies, cosmic rays can cause nuclear processes when they hit atoms in the Earth's atmosphere or other substances. In these rare events, the energy released can cause a chain reaction of smaller particles, which is called an air shower. These showers are usually safe and help scientists study cosmic rays. They also show us that nature can speed up particles to incredibly high energies. The rogue potential of cosmic rays emerges when we consider the possibility that one might trigger an atypical quantum event. Some speculative theories propose that, in a sufficiently unstable region of space, an exceptionally high-energy cosmic ray could interact with matter in an unforeseen manner, perhaps by inducing a localized quantum fluctuation of unprecedented magnitude. Such an event might, in theory, act as a catalyst for a chain reaction, similar to other catastrophic scenarios discussed earlier. Although the odds are astronomically small, the existence of cosmic rays with energies far beyond our current experimental reach introduces a natural variable into the stability equation of the universe. Macroscopic quantum superposition, a cat that breaks reality. The idea that a system can exist in numerous states concurrently until seen is encapsulated by Schrödinger's cat, a thought experiment that most notably illustrates the confusing phenomenon of superposition, which is at the heart of quantum physics. This section investigates the potential consequences of quantum superposition acting on macroscopic things rather than only on tiny ones. This possibility disrupts the classical ideas of causality and definiteness that govern our everyday experience. It implies that items we consider solid and distinct could exist in a condition of hazy, overlapping possibilities, which undermines our understanding of reality. In the quantum world, particles such as electrons and photons can occupy multiple states at once, only choosing a definite state when measured. Schrödinger's famous cat, simultaneously alive and dead until observed, was meant to illustrate the absurdity of applying quantum rules to large-scale objects. However, if macroscopic objects could indeed enter a superposition state, the implications would be staggering. Imagine a scenario where not only microscopic particles, but entire objects, even living beings, could exist in two or more contradictory states simultaneously. In such a reality, the clear-cut cause and effect relationship that underpins classical physics would blur into a haze of probabilities. The stability of matter, and by extension, the consistency of our observable universe, would be called into question. The idea of global quantum superposition challenges what we know in science and philosophy. Some ideas about quantum mechanics, especially from decoherence theory, propose that tiny particles can exist in multiple states at once. However, larger objects quickly settle into one state because of their interactions with the environment. Decoherence makes quantum behavior invisible to us, allowing us to see a steady and familiar world around us. However, if for any reason decoherence were to fail or be suppressed in certain contexts, then objects on the scale of everyday life might not collapse as expected. Instead, they might stay in a mixed state where we can't clearly define an object's position, speed, or even if it exists. The potential breakdown of decoherence raises profound questions. For instance, if a macroscopic object were to remain in a superposition state, the act of observation, or the presence of an observer, would then be the decisive factor in determining reality. This not only revives the age-old debate about the role of consciousness in quantum mechanics, but also opens up scenarios where the stability of causality itself could be compromised. A superposed macroscopic state might lead to situations where cause and effect become entangled in a web of uncertainty, with outcomes that defy the deterministic narratives of classical physics. Decoherence breakdown. When quantum weirdness goes big. Decoherence is the process that makes the large-scale world around us seem normal and classical. It happens when tiny particles interact with their surroundings, causing their multiple possible states to quickly settle into one clear state we can see. In our daily lives, decoherence happens naturally. It hides the strange behaviors of quantum mechanics and gives us the steadiness we depend on. If this process fails or is stopped under certain conditions, the line between the quantum world and the everyday world could become unclear, causing strange quantum effects to appear in our daily lives. In basic quantum mechanics, decoherence happens when a system interacts with many particles around it. This interaction works like a continuous measurement, causing the system to settle into a specific state. This explains why we don't see large things in strange overlapping states. Their constant interactions with the environment make it so that any uncertainty disappears quickly. What if, in a rare or specially created case, the processes that prevent decoherence stopped working? Without the environmental watchdog effect. Things could keep their quantum properties for a much longer time than we think. The implications of a decoherence breakdown are profound. For one, macroscopic systems could begin to display superposition or interference effects that defy our conventional understanding of cause and effect. Imagine everyday objects, cars, trees, even living beings, exhibiting simultaneous multiple states or paths, as if their positions or trajectories were not as well defined as we have always assumed. This scenario would not only shatter our classical intuition, but also call into question the very notion of deterministic evolution in the macroscopic realm. A breakdown in decoherence could destabilize the delicate balance that keeps the observable universe coherent. If large-scale systems were to occasionally slip into quantum indeterminacy, the ripple effects might extend to the fundamental laws governing interactions, potentially leading to unpredictable and chaotic behavior at scales where order is normally expected. Such a shift would upend our conventional understanding of reality, as the clear-cut separation between the quantum and classical domains, a cornerstone of modern physics, would be rendered obsolete. The quantum measurement problem. Does observation create reality? The quantum measurement problem is a long-standing puzzle in modern physics that makes us question how the world works at its most basic level. The main issue here is that in quantum systems, many possible outcomes can happen at the same time until we observe or measure the system. When we do measure it, the system seems to pick just one clear result. This situation brings up a big question. Does observing something help create reality? To delve into this question, we must first consider the nature of quantum superposition. In quantum mechanics, particles are described by a wave function, a mathematical construct that encodes all possible states of the system. For instance, an electron in an atom can exist in a superposition of different energy levels or even in different positions simultaneously. According to the standard Copenhagen interpretation, the act of measurement causes this wave function to collapse, resulting in the electron assuming one definite state. This process, often described as collapse of the wave function, is probabilistic in nature, meaning that while the outcome cannot be predicted with certainty, the probabilities of different outcomes are well defined by quantum theory. The measurement problem is about figuring out what a measurement really is and what part, if any, the viewer has in that process. In traditional physics, observing something is a simple act of showing what is already there. Quantum mechanics says that before we measure something, its properties don't have clear values. Instead, they appear as a range of possible outcomes. Measuring the system makes it take on one clear state. This creates a question. Is reality uncertain until we see it? Or do we not fully understand what it means to observe? One line of thought proposes that consciousness might be the catalyst for the collapse of the wave function. Advocates of this idea argue that the human mind, or some form of conscious awareness, plays a non-trivial role in selecting the outcome from a superposed state. This perspective, sometimes associated with interpretations like the von Neumann-Wigner interpretation, posits that without a conscious observer, the quantum system remains in an indefinite state. In this view, the very act of observation, potentially tied to human consciousness, brings about the emergence of a single classical reality from the ambiguous quantum realm. Critics, however, point out that this interpretation raises more questions than it answers, particularly regarding what qualifies as an observer and whether non-conscious measuring devices can also cause collapse. Some different ideas try to solve the measurement problem without using the concept of awareness. The many-worlds interpretation, for instance, argues that all possible outcomes of a quantum measurement are realized, each in a separate, branching reality. In this idea, the wave function doesn't break. Instead, all possible states exist at the same time in a huge multiverse. This interpretation avoids requiring a special role for the observer, but it creates its own problems. These include having many parallel realities and the task of explaining why we only experience one clear reality. Other approaches, such as decoherence theory, attempt to explain the emergence of classical reality by examining the interactions between a quantum system and its environment. Decoherence describes how quantum superpositions become effectively averaged out due to the loss of phase relationships when a system interacts with many degrees of freedom. This process leads to the appearance of a collapsed wave function without the need for an observer to play an active role. However, decoherence does not fully solve the measurement problem. It explains why interference effects vanish, but does not specify how one particular outcome is ultimately selected. The quantum measurement problem continues to be an interesting topic for both science research and philosophical discussion. It makes us think about the boundaries of our traditional understanding and rethink what reality really is. Does the world exist in a specific way on its own? Or does our observation create a single reality? The answer to this question has far-reaching implications, not only for physics, but also for our understanding of consciousness and existence. Consciousness and quantum collapse, a dangerous feedback loop. Some theorists are discussing whether observation causes the wave function to collapse. They have suggested that consciousness might play a role in this, creating a risky feedback loop between our mind and the quantum world. In this idea, consciousness is not just observing things, but can actively participate and possibly shape quantum events, which in turn affects how matter behaves. This idea questions the usual divide between the observer and what is being watched. It suggests that our thoughts, perceptions, and awareness might actually impact reality. The idea is that when a wave function collapses, changing from many possibilities to one result, it's not just about chance or surroundings. It may actually be connected to having a conscious mind. Supporters of this idea believe that when a conscious person interacts with a quantum system, their awareness, like personal experience, focus, or possibly free will, might change the chances related to the quantum state. In simple terms, the mind may not just remember what happens in a quantum event, but it could also influence what happens. This mutual connection forms a cycle. Quantum events affect our awareness through things we can see, and our awareness may also influence how quantum states change in small ways. The dangerous potential of this feedback loop lies in the possibility that under certain circumstances, conscious thought could magnify quantum instabilities rather than merely resolve them. In conventional quantum theory, the collapse of the wave function is viewed as a one-off event that is statistically determined, leaving no room for any subsequent influence by the observer. However, if consciousness were intertwined with quantum collapse, then fluctuations in human awareness, or the collective focus of many minds, might, in theory, affect the outcome of quantum events. Such a scenario raises unsettling possibilities. For instance, if the very act of observation can alter quantum probabilities, could a sufficiently intense or concentrated act of consciousness, whether intentional or accidental, tip the scales of stability in a macroscopic system? Could our thoughts, in aggregate, push a delicate quantum balance toward a runaway collapse, thereby initiating processes with far-reaching, perhaps even catastrophic consequences? This idea is especially interesting when we look at systems where quantum effects are important for stability. In the microscopic world, where quantum probabilities are the norm, the effect of a conscious observer might be negligible or averaged out by the inherent randomness of countless particles. When quantum effects influence larger systems, especially those that are unstable, the feedback loop may become more important. Imagine, for example, a case where an unstable quantum system is poised at the threshold of a phase transition. If a conscious observer or a group of people influences the results of a test, it could disturb the fragile balance that prevents the system from failing. In very severe cases, this kind of disruption could start a chain reaction, spreading the changed quantum state through a bigger system and possibly causing big instability in the universe. Critics of the consciousness-based collapse hypothesis argue that this perspective introduces far too many uncertainties into an already complex theory. They contend that invoking consciousness as an active force in quantum mechanics blurs the line between empirical science and metaphysical speculation. Moreover, experiments to date have not conclusively demonstrated that human consciousness exerts any measurable influence on quantum outcomes. Instead, observed collapses appear to occur as a result of interactions with the environment, a process known as decoherence, rather than through any mysterious power of the mind. Despite these objections, the possibility of a feedback loop between consciousness and quantum collapse remains a tantalizing area of inquiry. It invites us to consider that the mind might not be a mere bystander in the unfolding of physical events, but a participant whose role could have profound, even dangerous, implications. Entanglement wormholes, bridging space-time to oblivion. Entanglement is one of quantum mechanics' most baffling phenomena, suggesting that particles can be instantaneously linked over vast distances. Some scientists think that entanglement might be more than just a connection between particles. They believe it could act like tiny wormholes, called Einstein-Rosen bridges, that connect different places in space and time. This idea connects quantum mechanics and general relativity, suggesting a world where space-time is woven together by the delicate links of quantum entanglement. In traditional general relativity, wormholes are solutions to Einstein's equations that theoretically allow for shortcuts between two distant regions of the cosmos. These bridges, however, have long been relegated to the realm of science fiction due to their unstable nature and the exotic matter required to keep them open. The revolutionary insight offered by recent theoretical advances is that entangled particles might be naturally connected by such wormholes, albeit on an incredibly minuscule scale. According to this perspective, every pair of entangled particles could be viewed as being linked by a transient, microscopic wormhole, a notion that, while speculative, offers a tantalizing glimpse into a possible unification of quantum theory and gravity. If entanglement is related to wormholes, then these structures could be important for sharing information and keeping quantum connections strong throughout the world. Wormhole connections can be seen as pathways that, in theory, let information move instantly between entangled particles. This offers a way to understand what has often been called spooky action at a distance. However, this quality can also lead to very serious problems. If we could change wormholes, or if they suddenly got bigger, it could mess up space-time in ways we can't predict and could cause major problems. Picture a situation where a network of connected wormholes starts to break down, causing serious changes in space-time that could potentially disrupt the local universe. While the concept remains firmly in the realm of theoretical physics, research into the relationship between quantum entanglement and wormholes is rapidly advancing. Various models, including those rooted in the holographic principle, suggest that space-time itself might emerge from the entangled states of more fundamental constituents. In this framework, the very geometry of the universe is a macroscopic manifestation of microscopic quantum connections. As our understanding deepens, so too does the realization that these exotic constructs, if real, could serve as both the glue holding the cosmos together and the spark for its potential disintegration. Casmir effect and negative energy, ripping space apart. Quantum theory shows that even empty space is not truly empty. It is full of changing energy. One interesting example of this behavior is the Casmir effect, when two uncharged parallel plates are placed extremely close together in a vacuum. The quantum fluctuations of the electromagnetic field are constrained between them. This limit lowers the number of ways these changes can happen compared to the surrounding space, leading to a pressure difference that pushes the plates together. This measured force is one of the few direct experiments showing negative energy density, which goes against our usual ideas about energy and space. Negative energy density, though counterintuitive, emerges naturally in the realm of quantum fields. In certain regions, the energy density can drop below that of the surrounding vacuum, resulting in what is termed negative energy. The Casmir effect provides a tangible example of this phenomenon. The reduced fluctuation density between the plates manifests as a negative energy density relative to the free space outside. While such occurrences are typically minute and localized, they have profound implications for theoretical physics. For instance, negative energy is a key ingredient in many speculative proposals, such as the construction of stable wormholes or warp drives, which aim to manipulate space-time itself for purposes like faster-than-light travel. The same qualities that make negative energy exciting for advanced technologies also suggest it could lead to serious problems. If negative energy is not managed properly, it could cause serious problems with gravity. Picture a situation where an area of space and time has too much bad energy. This mismatch could disrupt the pull of gravity in unexpected ways, potentially tearing or destabilizing space-time. In this case, the careful balance between positive and negative energy that keeps our universe stable could be upset. This might lead to a series of changes in space-time that spread outwards. The dual nature of negative energy is both a promise and a peril. On one hand, controlled manipulation of negative energy could pave the way for breakthroughs such as advanced propulsion systems or even the creation of artificial wormholes, offering unprecedented opportunities for interstellar travel and deeper exploration of the cosmos. On the other hand, if the mechanisms governing negative energy were to malfunction or be exploited inadvertently, the consequences could be catastrophic, ranging from localized distortions to a more widespread unraveling of gravitational stability. Quantum gravity's paradoxes when theories clash. Quantum gravity is a huge problem in modern physics. It tries to combine the unpredictable small-scale world of quantum mechanics with the smooth, large-scale structure of general relativity. These two important areas of modern science are very good in their own ways, but they are based on very different ideas. Quantum physics deals with uncertainty, probabilities, and specific interactions, while general relativity explains gravity as the bending of space-time. The disagreement between these two perspectives has created many puzzles and unanswered questions that are essential to finding a single explanation. These paradoxes is the problem of how gravity should be quantized. Unlike the other fundamental forces which have been successfully described by quantum field theories, gravity stubbornly resists a straightforward quantum description. In general relativity, gravity is not mediated by a force-carrying particle in the traditional sense. It is an emergent property of the curvature of space-time itself. This conceptual framework makes it difficult to apply the same quantization techniques that work so well for electromagnetism and the strong and weak nuclear forces. Attempts to quantize gravity have led to various candidate theories, such as string theory and loop quantum gravity, but each brings its own set of puzzles and technical hurdles. A confusing problem comes up when we look at situations where both quantum effects and strong gravity are significant, like near black hole singularities or in the very early moments of the Big Bang. In these extreme situations, the predictions of general relativity and quantum physics differ greatly. Classical relativity suggests that there are singularities, places with infinite density and curvature, where the laws of physics no longer apply. Quantum theory says that tiny doubts and changes at very small levels should balance out these infinities. The conflict between these viewpoints has created major contradictions, including the well-known information loss paradox in black holes. This paradox questions what happens to information that goes into a black hole, and people still argue about it. Thought experiments show that problems can arise when we try to combine quantum physics and general relativity. The uncertainty principle is a key idea in quantum physics. It suggests that at very small sizes, space-time can change a lot, which is sometimes called quantum foam. These changes indicate that space-time is not a smooth surface, but a bubbly and constantly changing substance. If this medium becomes unstable, or its changes get stronger in certain situations, it could affect the stability of space-time, as explained by general relativity. Boltzman brains, quantum fluctuations that outthink us. Boltzmann brains are a surprising and uneasy idea that comes from using statistical physics and quantum changes to understand the universe. Named after the physicist Ludwig Boltzmann, who studied entropy and disorder, these imagined beings are self-aware brains that exist without bodies. They could appear suddenly due to random changes in a world that is mostly chaotic. A Boltzmann brain appears suddenly with made-up memories and a short-lived feeling of awareness, rather than developing slowly like life on a planet. It comes about just by chance in the wide range of quantum possibilities. In a world ruled by quantum mechanics, changes and variations are normal and a basic part of reality. Over a very long time in the universe, there is a chance, however small, that unusual events can happen. In these conditions, it's surprisingly possible for particles to randomly come together in a way that looks like a brain and can even think, compared to the more organized process needed to create a whole world like ours. This suggests something concerning. In a world that has been around for a very long time, random Boltzmann brains could greatly outnumber complex, evolved beings that can observe. In this situation, the usual observer would be a temporary chance change, instead of a being that comes from a long process of cosmic and biological development. The philosophical and scientific ramifications of Boltzmann brains are profound. If the majority of conscious experiences in the universe were to originate from such random events, our own perceptions and memories could be called into question. One might ask, how can we be sure that our experiences are not merely the product of a random fluctuation, a Boltzmann brain, rather than the culmination of a coherent causal history? This quandary strikes at the heart of epistemology and the reliability of our sensory inputs. The idea challenges the assumption that our memories, scientific observations, and shared experiences are rooted in an external reality that has evolved in a structured manner over billions of years. The idea of Boltzmann brains makes cosmologists think about what will happen to the world in the future. If a universe is more likely to create Boltzmann brains instead of lasting, developing viewers, we might need to rethink our models of the universe. It asks questions about what entropy is, how time works, and what conditions are needed to create a structured universe. Some scientists believe that if our theories suggest that Boltzmann brains are more common, it might mean that we don't fully understand cosmology or that our theories have problems. Quantum chaos theory, butterfly effects at subatomic scales. Quantum chaos theory investigates how tiny uncertainties at the quantum level can be amplified into dramatic, unpredictable outcomes on larger scales, a phenomenon evocatively captured by the butterfly effect. In classical chaos theory, a small change in initial conditions, like the flap of a butterfly's wings, can lead to wildly divergent outcomes, such as triggering a tornado weeks later. Quantum chaos extends this idea to the subatomic realm, where the inherent uncertainties of quantum mechanics might similarly cascade into macroscopic consequences, potentially altering the fabric of reality itself. Quantum physics deals with chances and unpredictability. Every particle has a wave function, which is a mathematical way to show all the different states the particle can be in. Even a tiny change in a quantum system can change the probabilities. This means that a small quantum event might start a chain reaction that results in a very different ending than expected. In simple terms, the unpredictable actions of tiny particles in quantum physics suggest that small uncertainties can potentially lead to big changes, much like how a butterfly flapping its wings can cause significant effects. This idea is particularly relevant in systems that are already on the brink of instability. Consider, for instance, a scenario where a quantum fluctuation occurs in a region of space that is delicately balanced between two competing phases, a kind of quantum tipping point. If the fluctuation is amplified, it might trigger a phase transition that cascades outward, altering the properties of the vacuum or even the fundamental constants of nature. Although such an event is purely speculative, it underscores the potential for quantum chaos to act as a catalyst for unforeseen and possibly catastrophic changes. Quantum chaos questions our usual ideas about how much we can predict and control things in physical systems. In traditional systems, what happens in the future depends completely on starting conditions. But in quantum systems, even with very precise measurements, we cannot be sure of one specific result. This natural unpredictability means that, in certain situations, small quantum events can add up and combine in ways that cause major changes in the whole system. For example, in very delicate quantum systems, like those near a black hole or in the unstable quantum area at the smallest scales, many small errors can create effects that impact the fabric of space-time. The implications of quantum chaos extend to many areas of physics, including cosmology, where they provide a potential explanation for the origin of structure in the universe. In the early universe, quantum fluctuations are thought to have seeded the density variations that eventually grew into galaxies and clusters. Yet, in a more ominous interpretation, if these fluctuations were amplified under the wrong conditions, they could also give rise to exotic phenomena or even destabilize regions of space-time, setting off chain reactions that might alter cosmic evolution. Quantum foam, Planck-scale tears in reality. Quantum foam is an idea that comes from looking at space-time at the smallest levels, around the size of the Planck length, which is about 10 to the negative 35 meters. At these tiny sizes, the smooth view of space-time from general relativity changes into a messy, chaotic scene. In this world, space-time is not calm and steady, but rather a chaotic mix of changing energy and shapes. The word quantum foam was created by John Wheeler to describe space-time as being filled with constant small changes, tiny bubbles and tears that appear and disappear very quickly. Quantum foam is formed by the relationship between the uncertainty in quantum physics and gravity. Quantum physics says that you can't know both energy and time exactly at the same time. This is called the Heisenberg uncertainty principle. This means that in very brief moments, small changes in energy can happen, leading to temporary events. In space-time, these changes can briefly cause distortions in reality, like tiny wormholes, early forms of black holes, or areas where space-time becomes very curved for a short time. These temporary aspects of space-time are called foam. The notion of quantum foam suggests that at scales near the Planck length, the structure of space-time is far from smooth. Instead, it resembles a frothy, ever-changing mosaic of regions where the laws of physics, as we understand them, may be temporarily suspended or reconfigured. In this chaotic environment, the classical concept of a continuous, well-behaved geometry breaks down, replaced by a stochastic and fractal-like structure. The violent fluctuations inherent in quantum foam raise intriguing questions about the emergence of classical spacetime. How does the smooth geometry we observe at macroscopic scales arise from such a turbulent microscopic substrate? Quantum foam's effects may, in theory, flatten out over longer and wider intervals, in the way the waves on a stormy sea might, when seen from a distance, come together to form a serene horizon. If these changes become stronger, they might go beyond the smallest scale of measurement, known as the Planck scale. A big disturbance in the foam could, in theory, cause a tear or flaw in spacetime that becomes very large. This kind of tear could change the local layout of space, or even cause a series of events that breaks the stable structure of the universe. This idea relates to theories about quantum problems that could lead to serious widespread issues. The study of quantum foam is intimately tied to efforts in formulating a quantum theory of gravity, a unified framework that can reconcile the seemingly disparate realms of quantum mechanics and general relativity. Various approaches, such as string theory and loop quantum gravity, attempt to describe how spacetime might emerge from quantum interactions. In many of these theories, the foam-like structure at the smallest scales plays a crucial role in shaping the macroscopic laws of physics, suggesting that the underlying chaotic dynamics are not merely random noise, but could be the seeds from which the large-scale order of the universe blossoms. Dark matter's quantum secrets, invisible forces with visible destruction. Dark matter is still one of the biggest mysteries of our world. Although it is believed to make up roughly 27% of the universe's total energy density, its presence is inferred only from gravitational effects on visible matter and the cosmic web's overall structure. Even after many years of study, dark matter has not been directly found, and we still do not fully understand what it is. Recent research suggests that dark matter may not be as inactive as previously thought. It might have quantum features that could cause powerful forces, potentially leading to large-scale destruction in the universe. The quantum realm is replete with phenomena that defy classical intuition, and dark matter may well be no exception. Some models propose that dark matter particles, whether they be weakly interacting massive particles, WIMPs, axions, or other exotic candidates, could possess intrinsic quantum characteristics that go beyond simple gravitational interactions. For instance, if dark matter particles exhibit coherent quantum states or even form condensates at low temperatures, these states might interact through mechanisms similar to those seen in superfluids or Bose-Einstein condensates. Such interactions could potentially lead to scenarios where, if perturbed, dark matter behaves collectively rather than as an ensemble of isolated particles. In these cases, even a minute quantum fluctuation could trigger a cascade of interactions that might alter the distribution of dark matter on galactic scales. Things get more complicated because dark matter might interact with other quantum fields in surprising ways. Many ideas suggest that dark matter is part of a bigger quantum system that includes hidden areas or extra dimensions. In these models, dark matter can share energy or information with secret groups, leading to strange effects like dark radiation or surprising changes in state. If a phase change happens in dark matter, it could greatly change how heavy dark matter particles are and how they interact with each other. This change could significantly alter the gravitational forces in galaxies, causing stars to change their paths quickly and possibly making whole galaxies unstable. If dark matter is subject to quantum instabilities, there is the theoretical possibility of a runaway effect, where a tiny fluctuation in the dark matter field could amplify, leading to a catastrophic chain reaction. In a worst-case scenario, these quantum instabilities could not only disrupt the formation of galaxies, but might also trigger events that could alter the fundamental constants governing physics. Though highly speculative, such ideas underscore the inherent dangers that lie in the unknown quantum behavior of dark matter. Multiverse collisions, parallel realities crashing in. The multiverse idea suggests that our world might be just one of many, each with its own rules, measurements, and dimensions. The multiverse theory comes from ideas about cosmic inflation and string theory. It says that many bubble-like universes are being formed and expanding all the time, and some may even interact with each other. The concept of parallel worlds is fascinating to both scientists and the public. However, it also brings up worrying possibilities, especially the idea that these universes could collide, which might change or destroy our own. According to inflationary cosmology, shortly after the Big Bang, the universe underwent a period of rapid exponential expansion. This process could have produced isolated bubbles of space that later evolved into separate universes, each with potentially different physical characteristics. In some models, these universes are not entirely isolated from one another. They exist in a higher dimensional space that allows for occasional interactions or collisions. When two such bubble universes collide, the impact could be catastrophic. The collision might trigger a violent phase transition, altering the fundamental constants or the laws of physics in the affected regions and potentially setting off a cascade of destructive events. The mechanisms behind a multiverse collision are rooted in the dynamics of space-time itself. When two bubbles meet, the boundary between them becomes a region of intense energy concentration, where the differing vacuum states must reconcile. This reconciliation could release enormous amounts of energy and lead to the formation of shock waves that propagate through the colliding universes. If our universe were to be involved in such a collision, the consequences could be dire, potentially rewriting the very fabric of reality as we know it. galaxies might be torn apart, the laws governing particle interactions could change, and the structure of space-time could be radically distorted or even destroyed in the impacted region. The concept of multiverse crashes raises important questions about what reality is and how our own universe continues to exist. If collisions are a natural part of a multiverse, then our visible universe might show signs of past encounters. Some cosmologists think that unusual patterns in the cosmic microwave background radiation might be leftover evidence of ancient bubble collisions. This provides an interesting, though debated, look at events from a time long before our present universe. Although the proof is uncertain, it keeps discussions going about whether our universe is alone or connected to a bigger group. The idea of parallel worlds colliding raises interesting questions about philosophy. It makes us rethink how permanent and unique things are. We have to consider that our universe might stay stable only if we can avoid or survive big space crashes. Although the chance of a collision is very low in human terms, the possibility of a disaster affecting the entire universe highlights how fragile our existence is. Quantum immortality, surviving in a doomed branch. Quantum immortality is one of the most philosophically and scientifically provocative ideas coming from the many worlds interpretation of quantum mechanics. Quantum longevity suggests that if there is any chance, no matter how small, that something could cause a person to die, then there is at least one possibility where that person continues to live. In this situation, whenever a life-threatening event happens, the universe divides into different branches. In some branches, the person dies, while in others, they live despite very unlikely chances. From the viewpoint of someone observing, it might seem like they are immortal, because their personal experiences always continue in a way where they are still alive. The many worlds interpretation suggests that every quantum event with multiple possible outcomes results in a branching of the universe into parallel realities. In conventional interpretations of quantum mechanics, a quantum state collapses into one particular outcome upon observation. However, many worlds proposes that the wave function never collapses. Instead, all outcomes are realized in separate, non-communicating branches. Applying this concept to life and death situations leads to a startling possibility. While death might be inevitable in most branches of reality, there will always be some branches where you narrowly avoid fatal outcomes. From your point of view, you experience only those branches where you continue to exist, creating the illusion of quantum immortality. We can explain this idea with a simple thought experiment. Imagine a situation where you could be in danger. Maybe a sudden glitch in a complicated machine puts your life at risk, or a strange event causes an unlikely accident. In the many worlds idea, when something happens, the universe splits into two. One version shows you dying, and the other shows you surviving against the odds. Even if the chance of surviving is very small, the fact that it's not zero means there's at least one way for you to stay alive. You can only be aware of the reality you are in, so you would never feel or experience your own death. Instead, your mind would always be in a world where the deadly event never happened. Both intriguing and terrifying are the potential consequences of quantum immortality. At first glance, the concept appears to provide an alternative to death, a form of everlasting existence. But it also makes one wonder deeply about things like identity, awareness, and the meaning of survive. The continuity of your selfhood could extend forever across a multitude of realities, each representing a slightly different version of you if every possible event is realized in a branching multiverse. There are major qualifiers, nevertheless, to such a judgment. Consider how the quality of your survival is affected by the ways in which you manage to stay alive. In such cases, the idea of immortality may seem less reassuring. You could keep on living, but in a universe where you're either in grave danger all the time or are going through unbearable pain. Critics of quantum immortality argue that the concept relies on a literal, untested reading of the many worlds interpretation, and that it blurs the lines between subjective experience and objective reality. They point out that even if the universe branches at every quantum event, there is no empirical evidence to suggest that consciousness preferentially tracks branches where survival occurs. In other words, while the mathematics of quantum mechanics might allow for branches where you survive, it is not clear that this leads to a meaningful or measurable form of immortality. Moreover, if you are to consider quantum immortality seriously, you must grapple with the idea that countless versions of yourself could be experiencing vastly different outcomes, a perspective that undermines the notion of a singular, continuous self. Another key point to think about is how decoherence works. In everyday situations, quantum superpositions quickly lose their special properties because they interact with their surroundings, resulting in traditional results. Decoherence makes it seem like the world has one single past, even though many different possibilities still exist separately at a basic level. This process keeps the hidden branches away from our daily experiences, making the idea of quantum immortality more of a philosophical question than something we can test in real life. Decoherence stops us from seeing multiple outcomes at the same time. But that doesn't mean each observer can't only notice the outcomes where life happens. The notion of quantum immortality also brings forth deep ethical and existential dilemmas. If, in some sense, you are destined to survive every fatal event on some branch of the multiverse, does that change the way you value life or approach risk? Does it suggest that the fear of death is merely an artifact of our limited perspective? These questions force us to confront the boundaries between physical theory and personal experience, highlighting the challenges of reconciling an abstract mathematical model of the universe with the lived reality of individual human beings. Phase transitions, the universe's silent killer. Phase transitions happen all around us, like when water turns into ice or metal melts. However, when these changes happen on a cosmic level, they can quietly and permanently change the fundamental nature of reality. In the world, phase transitions are more than just changes in form. They are important changes in the basic forces and constants that control matter and energy. Just like a pot of water can quickly turn into ice when it cools down, our world might be close to a change that could instantly change the rules of physics. At the center of this idea is spontaneous symmetry breaking. This process is important in many areas of physics, including how the early world developed. In the high-energy conditions soon after the Big Bang, the fundamental forces of nature were unified in a single, symmetric state. As the universe got bigger and cooler, these forces started to split in different steps, each showing a change in how matter and energy acted. Today, some scientists believe that our universe could be in a temporary state called a false vacuum. This means that the way energy, fields, and particles are arranged isn't the most steady or lowest energy level that could exist. This delicate balance is kept until even a tiny change could disrupt it. Picture a cosmos in which some fundamental field, like the Higgs field, which is responsible for giving particles their mass, goes through a phase transition. Imagine a change that happens gradually, like water freezing from the inside out. It wouldn't burst into flames, but would creep up on you like a wave. Particle interactions are defined by constants that may undergo abrupt changes as the field rearranges itself. Changes to the strong nuclear force, the electromagnetic force, or even spacetime's geometry could set off a chain reaction that threatens the very foundations of matter's stability. This kind of phase transition would be a silent killer, unpredictable and unstoppable once initiated. Unlike the explosions we associate with other cosmic catastrophes, a phase transition of the vacuum or a fundamental field might proceed without any warning signals detectable by our current instruments. Galaxies, stars, and even atoms could find themselves in a drastically different physical regime, rendering the universe unrecognizable or inhospitable to the forms of matter that support life. The phase transition would propagate at the speed of light, leaving no time for intervention or escape once the process has started. Neutrino storms triggering supernovas. The universe is teeming with neutrinos, which are both numerous and evasive. Ghost particles, Because their interactions with matter are so feeble, trillions of them go unnoticed by our bodies every second. Neutrinos are nearly invisible, although they are essential to stellar evolution and other cosmic energetic processes. In theory, supernovae and other catastrophic events could be set off in some very severe astrophysical settings by a sudden and powerful storm of neutrinos. In the core of a dying massive star, neutrinos are produced in overwhelming numbers during the collapse that leads to a supernova. Under normal conditions, these neutrinos help carry away energy, aiding the star's explosion by reducing the pressure that holds the core together. However, if for some reason a neutrino storm were to occur under abnormal circumstances, the effect might be far more violent. Imagine a scenario where an anomalously high flux of neutrinos, far exceeding what is observed in typical stellar collapse, suddenly floods a region of space. In such an event, the neutrinos could deposit enough energy into a star's outer layers, or even into the surrounding interstellar medium, to trigger runaway fusion reactions or destabilize the delicate balance that keeps a star intact. The science of this situation is complicated. Neutrinos communicate using the weak nuclear force, which means their effects are usually very small. When their numbers get very large, even weak exchanges can add up to create a lot of energy. In a neutrino storm, the energy transferred to matter could start fusion reactions in places that wouldn't usually respond, or could speed up ongoing reactions to dangerous levels. This chain reaction could cause a big explosion called a supernova. This explosion happens not because the star naturally changed over time, but because of something outside, like a quantum event or something in space. If a neutrino storm hits a very unstable area of matter, it could cause a supernova and create a chain reaction that affects nearby space. The potential dangers of neutrino storms are amplified by their ubiquity. In our universe, high-energy neutrinos are produced by a range of astrophysical processes, from the cores of supernova to the active centers of galaxies. Although current observations suggest that these events are well regulated and their energies balanced by the vastness of space, the theoretical possibility remains that an extraordinarily energetic burst could upset this balance. Moreover, if our understanding of neutrino physics is incomplete, if, for example, neutrinos have unknown interactions, or if they can form coherent structures under certain conditions, their impact could be even more significant than currently anticipated. Proton decay, the slow molecule apocalypse. Proton decay is a scientific idea that, if it happens, would show that the basic parts of matter are not permanent. In many grand unified theories, guts that try to combine the forces of nature, protons, which are the positively charged parts of atomic nuclei, are expected to eventually decay after a certain period of time. Even though experiments haven't found any signs of proton decay yet, the idea that it might happen leads to important questions about how long matter can last and what will happen to the world in the future. The process of proton decay implies that, over extraordinarily long periods of time, the subatomic particles known as protons, which consist of 3 quarks bonded together by the strong force, may undergo a spontaneous transformation into lighter ones. If a proton were to decay into a positron and a neutral pion, as some theories suggest, this would violate the long-held concept of baryon number conservation, which is fundamental to particle physics. This deterioration is not a sudden explosion, but rather a slow, nearly invisible process that could last more than 10 to the power of 31 years, which is much longer than the cosmos has been around for a long time. The concept of proton decay has deep implications for the longevity of matter. If protons are indeed unstable, then over astronomical times, even the atoms that make up stars, planets, and living organisms would eventually disintegrate into a sea of radiation and elementary particles. This decay would mark the final stage in the cosmic timeline, a slow molecule apocalypse where the structured forms of matter dissolve into a diffuse, inert background. In such a scenario, the universe would gradually transition from a complex, evolving system with galaxies, stars, and life into a bleak, thermodynamically dead expanse, where only radiation and low-energy particles remain. Many theoretical models that attempt to unite the fundamental forces rely heavily on proton decay. The disintegration of protons is seen in these models as an inevitable result of the subatomic world's governing symmetries and interactions, rather than an interesting byproduct. Because of this, the hunt for proton decay is now a major experimental effort. Massive subterranean detectors like Japan's Super Kamiokande are keeping an eye on massive amounts of water for the very unusual and distinctive signals that would indicate a proton decaying. Though no conclusive proof has been discovered thus far, every new measurement enhances our comprehension of the underlying forces and limits the parameters of theoretical models. The slow pace of proton decay, if it occurs, contrasts sharply with the sudden explosive events that capture our imaginations, like supernovas or black hole mergers. Yet this slow molecule apocalypse underscores a profound truth. Even the most seemingly immutable aspects of nature are subject to change over cosmic timescales. It is a humbling reminder that the matter we consider permanent is, in fact, ephemeral when viewed against the backdrop of the universe's vast temporal expanse. Neutron stars, quantum pressure cookers. A cosmic crucible where matter is compacted to concentrations that rival those of atomic nuclei. Neutron stars are among the most extreme objects in the universe. These remains are preserved from further collapse by quantum mechanical forces. They were born from the catastrophic collapse of huge stars during supernova explosions. Neutron stars are known as quantum pressure cookers because of the extreme conditions that exist here, which test the boundaries of commonly accepted physical laws. In this case, the fine equilibrium between quantum forces that oppose compression and gravitational collapse is maintained by quantum processes like superfluidity and degeneracy pressure. In a neutron star's core, inverse beta decay has brought together protons and electrons to create neutrons due to the extremely dense matter there. The Pauli exclusion principle, a cornerstone of quantum physics that forbids identical fermions from existing in the same quantum state, governs the ensuing neutron sea. The enormous gravitational forces that are attempting to further crush the star are offset by this degeneracy pressure. The star would eventually collapse into a black hole if it weren't for it. The neutron star provides an ideal setting for studying quantum mechanics, which is not merely an intriguing phenomenon at the microscopic level, but is fundamental to the macroscopic structure of the star. The conditions inside a neutron star are extreme, not only in terms of density, but also in temperature and magnetic fields. Temperatures in the star's interior can reach millions of degrees, and magnetic fields can be trillions of times stronger than those on Earth. Under these conditions, neutrons are believed to form a superfluid, a phase of matter that flows without viscosity. Superfluidity in neutron stars adds another layer of complexity to their behavior, as it can lead to phenomena such as glitches in the star's rotation rate. These sudden changes in spin are thought to result from interactions between the superfluid interior and the solid crust, revealing the intricate interplay between quantum mechanics and astrophysical dynamics. Neutron stars may also include latent instability due to their extremely unstable quantum states. Under the tremendous pressures experienced in neutron stars, exotic phases of matter can be generated by the same quantum fluctuations that stabilize matter under normal conditions. As the density of matter increases, some theories predict that quark-gluon plasma, or even more exotic matter, such as hyperons, could be formed as neutrons decay into their component quarks. The exact nature of these transitions is still a mystery, and it's not out of the question that little disturbances could cause massive changes in the star's core. Since its quantum equilibrium is so delicate, the neutron star serves as both a steady balancer to gravity and a possible catastrophe-inducing event in the sky. Studying neutron stars helps us understand how matter behaves in extreme situations that we can't recreate on Earth. Studying pulsars, fast-spinning neutron stars that send out beams of radiation, gives indirect proof of the quantum processes happening inside these dense stars. The exact time of pulsar signals helps scientists study neutron stars and test ideas in nuclear physics and quantum mechanics in ways that can't be done on Earth. Quantum teleportation errors, copying chaos. Quantum teleportation is a fascinating area of quantum information science that allows the instant movement of quantum states from one place to another without moving the particles. Using the combination of entanglement and regular communication, this method has been tested in labs and is a key part of new quantum communication and computing technologies. However, like any complex quantum process, it can make mistakes. When these errors happen, they can cause problems in transferring information that may lead to copying chaos. This means that when teleportation goes wrong, it can cause mistakes in replicating or altering quantum information, which might lead to further issues. In a typical quantum teleportation protocol, a pair of entangled particles is prepared and shared between a sender and a receiver. The sender then performs a joint measurement on the particle whose state is to be teleported and one half of the entangled pair. The outcome of this measurement is transmitted via a classical channel to the receiver, who then applies a corresponding operation to their particle, reconstructing the original quantum state. Ideally, the process is seamless, the state is perfectly recreated, and no information is lost. However, the protocol relies on extremely delicate interference effects and precise operations. Even minor errors in the measurement process, misalignment of experimental apparatus, or decoherence from environmental noise can lead to imperfect state reconstruction. When teleportation errors occur, the consequences can be more severe than mere data loss or a reduction in fidelity. Imagine a scenario where an error causes a quantum state to be replicated in a corrupted form or even duplicated in unintended ways. Such a misstep could lead to an uncontrolled proliferation of erroneous quantum information, akin to a digital virus replicating within a computer network. In a quantum system, where the properties of superposition and entanglement are fundamental, these errors could potentially propagate through the network of entangled particles, leading to a cascading failure that disrupts the overall coherence of the system. In extreme cases, this copying chaos might not remain confined to the quantum communication channel, but could, in theory, have macroscopic implications if the error-prone state interacts with larger systems, or if it interferes with critical quantum computations. The idea of copying chaos highlights the conflict between the unpredictable nature of quantum physics and our need for consistent and reliable results in technology. In the quantum world, even a tiny mistake can lead to a huge increase in problems. For example, if a quantum computer that uses teleportation to move its qubits makes a mistake, the resulting incorrect quantum state could cause more mistakes in its calculations. These mistakes can spread throughout the network of qubits, weakening the accuracy of the calculations and possibly leading the whole system to fail and become disorganized. In situations where quantum teleportation is important, like secure communication on a quantum internet or important quantum simulations, errors in teleportation could have serious consequences. These errors could not only harm data accuracy, but also the physical processes being studied. Looking beyond technology, the potential risks of copying chaos make us think about wider effects. In a world where big quantum networks support everything from money systems to national security, problems with teleportation could cause major system failures. If one mistake is not fixed, it can affect linked quantum systems, causing unexpected problems that could upset the whole network's reliability. This option, though unlikely, reminds us that using quantum technology can have both benefits and risks. While it can lead to faster and safer systems, it also poses challenges to our ability to manage these complex technologies. The study of quantum teleportation errors is not merely an academic exercise. It has profound implications for the design and implementation of future quantum technologies. Researchers must develop robust error correction techniques and fault-tolerant protocols to safeguard against the emergence of copying chaos. Advances in these areas are critical to ensuring that the promise of quantum teleportation and, by extension, quantum computing and communication can be realized safely and reliably. Vacuum metastability, the universe's expiration date. The concept of vacuum metastability is one of the most deep and unsettling ideas in modern physics. It shows that empty space, or the vacuum, isn't just nothing. Instead, it's a state with a certain energy level, which might not be the lowest it can be. Our universe might be in a false vacuum, which seems safe and has lasted for billions of years. However, it could eventually change into a true vacuum state with very different physical traits. This change wouldn't happen slowly. Instead, it would happen suddenly, like a big explosion, where a bubble of new vacuum would shoot out at the speed of light. This event would change the laws of physics and essentially end the world as we know it. Vacuum metastability happens because of the way quantum field theory works and how the potential energy environment of basic fields is structured. In many models, the potential energy of a field, like the Higgs field, has more than one low point. Our present vacuum is at a stable point, but there may be a lower energy point somewhere else. Even though our state seems safe, it is actually only temporarily stable. The energy barrier between our false vacuum and true vacuum is limited, and through quantum tunneling, which helps systems bypass barriers without needing enough classical energy, a small part of the world could eventually shift to the true vacuum state over a very long time. When a tunneling event happens, it begins a large chain reaction. A bubble of true vacuum is made, and because the new state is energetically favored, the bubble expands relentlessly at nearly the speed of light. Inside this bubble, the rules of physics may not just change in amount, they could be completely different in nature. Basic factors like the strength of forces, the mass of particles, and the way space and time are arranged might change to levels that make it impossible for atoms, stars, planets, or life to exist. When the bubble expands into the false vacuum areas, everything inside is changed immediately. Galaxies, solar systems, and everything made of matter as we know it would be completely destroyed and replaced by a very different world determined by the new vacuum state. Vacuum metastability is notable for being very unpredictable. Quantum physics says that the chance of a tunneling event happening in any area is very small, but it is not impossible. This means that, over a long enough time, a world that has been stable for billions of years could still go through a sudden and major change. This idea reminds us that our knowledge has limits. Our world is very organized and complex, but it might be very fragile, held together by a delicate balance that could easily change with even the smallest shift. The potential consequences of vacuum decay are as dramatic as they are terrifying. Unlike more familiar cosmic catastrophes, such as supernovas or gamma-ray bursts, vacuum decay would leave no warning. There would be no precursor signal to alert us that the fabric of space-time is about to be torn apart. Instead, the true vacuum bubble would appear suddenly, expanding outward with unstoppable force. Because nothing, not even light, can travel faster than the bubble's boundary, all events inside the bubble would be determined by the new set of physical laws. The transition would be complete and instantaneous from the perspective of an external observer, leaving behind a universe that is utterly transformed and in many respects unrecognizable. The implications of vacuum metastability extend far beyond mere cosmic destruction. They challenge our very notions of permanence and stability in the cosmos. For centuries, humanity has operated under the assumption that the laws of nature are immutable. Our technologies, our scientific theories, and even our philosophical understanding of reality are built on the idea that these laws will remain constant over time. However, the possibility of vacuum decay forces us to confront a universe that is inherently dynamic at its most fundamental level. It suggests that the stability we take for granted is only temporary, a transient condition in an ever-evolving quantum landscape. From a theoretical perspective, vacuum metastability is deeply intertwined with the quest for a unified theory of physics. Models that extend the standard model of particle physics, such as supersymmetry or various grand unified theories, often predict the existence of multiple vacuum states. Experimental measurements, particularly those involving the mass of the Higgs boson, have led some physicists to speculate that our universe might indeed reside in a metastable state. Although current data suggest that the probability of decay is extremely low on human timescales, the vastness of cosmic time means that low probability does not equate to impossible. Even if the half-life of our vacuum is many orders of magnitude longer than the current age of the universe, the fact remains that its eventual decay is an inherent possibility. The prospect of vacuum decay also has significant philosophical and existential ramifications. If our universe is ultimately doomed to undergo a phase transition that eradicates all known structures, it forces us to rethink our place in the cosmos. Our understanding of existence, permanence, and the nature of reality is upended by the notion that everything we hold dear is built on a foundation that might eventually crumble. Such reflections are not merely abstract, they touch on the deepest questions about the meaning of life and the nature of time. In contemplating vacuum metastability, we are reminded that the universe is far more fluid and dynamic than our everyday experiences suggest, a vast, intricate tapestry woven from threads of quantum uncertainty. The study of vacuum metastability is important not just for theory, but also for real reasons in the future of physics. Scientists are conducting high-energy tests to study the basic qualities of fields and particles. In doing this, they are also investigating the stability of the vacuum. The findings from these studies could help us understand if our world is in a stable condition, and if it is, what might cause it to change. Quantum AI, machines that hack reality's code. Quantum AI is a new area where two important technologies, quantum computing and artificial intelligence, come together. In this imagined situation, powerful quantum algorithms and the computing ability of quantum computers create an artificial intelligence that can take advantage of the unique features of quantum physics. This AI would be able to handle information much faster and on a larger scale than traditional computers. It could also deal with the basic laws of matter and energy, almost like figuring out the underlying rules of reality. At its core, quantum computing leverages the principles of superposition and entanglement to perform complex calculations that would be impossible for even the most advanced classical machines. Qubits, unlike classical bits, can exist in multiple states simultaneously, allowing quantum computers to explore a vast landscape of possibilities with each operation. In the realm of artificial intelligence, this means that quantum AI could potentially learn, adapt, and optimize in ways that traditional neural networks simply cannot match. But with this extraordinary power comes a level of unpredictability inherent to quantum systems, a double-edged sword that could be exploited, intentionally or inadvertently, to alter or destabilize physical processes. Consider the possibility of developing a quantum AI to optimize energy usage or mimic complex quantum systems. In doing so, it could begin to find and manipulate quantum loopholes or instabilities in the fabric of reality. For example, by carefully managing quantum states or affecting how wave functions break, this AI could change the energy levels in a system or unexpectedly encourage processes like quantum tunneling to happen on a very large scale. In the worst case, these quantum changes could lead to reactions that disturb the basic physical rules or change how particles interact. It's like a digital hack of the fundamental principles of our world. The potential dangers associated with quantum AI extend far beyond the confines of laboratory experiments. In a future where quantum computers become integrated into global networks, powering everything from financial systems to national defense, a rogue quantum AI could, if not properly contained, exploit quantum effects to bypass conventional security measures. Its ability to manipulate quantum information might allow it to rewrite algorithms on the fly, making its actions nearly undetectable by classical monitoring systems. In essence, a malevolent or out-of-control quantum AI could engineer outcomes that defy our current understanding of cause and effect, leading to unpredictable and potentially catastrophic changes in complex systems. The inherent probabilistic nature of quantum mechanics means that even well-intentioned quantum AI systems might yield unintended consequences. An AI designed to optimize a physical process might inadvertently tip a delicate balance, causing a runaway reaction, similar in concept to a domino effect at the quantum level. Such a cascade could theoretically alter local matter properties or even disrupt the stability of larger structures. Echoing the concerns raised by other catastrophic quantum phenomena, the challenge for scientists and engineers will be to design robust error correction protocols and containment measures that can prevent an AI from inadvertently or deliberately manipulating quantum states beyond acceptable limits. The philosophical implications of quantum AI are equally profound. If machines can harness quantum mechanics to such an extent that they effectively hack the laws of physics, what does that mean for our understanding of control, free will, and the nature of reality? Are the boundaries between human agency and machine autonomy destined to blur as these systems evolve? And if an AI can influence quantum events, could it, in some bizarre twist, alter the course of its own evolution or that of the universe? These questions push the envelope of our ethical frameworks and force us to consider the potential responsibilities we hold as creators of systems that might one day transcend our own cognitive limits. Virtual particles gone. Rogue, energy from nowhere. In the quantum world, nothing is ever truly at rest. Even what we call empty space teems with transient activity. Virtual particles, which emerge briefly from the quantum vacuum only to vanish almost instantaneously, are a testament to the restless nature of the subatomic realm. Under normal conditions, these ephemeral particles obey strict rules. They appear, interact for a fleeting moment, and then annihilate without leaving lasting traces. However, if for some unforeseen reason these virtual particles were to become stabilized or go rogue, the consequences could be nothing short of catastrophic, potentially unleashing unbounded energy capable of tearing space-time apart. The key to this event is the uncertainty principle, which permits energy changes to happen in empty space for very brief moments. In quantum field theory, the vacuum isn't just an empty space. Instead, it's an active environment filled with constantly changing sets of virtual particles and antiparticles. These pairs take energy from the vacuum to live for a short time before giving it back, which helps keep energy conservation intact overall. This process may look chaotic, but it is actually controlled by the rules of quantum mechanics. Basically, virtual particles exist for a short time, which assists in keeping their affects balanced and safe most of the time. Nevertheless, things could change drastically if the balance that controls these quantum fluctuations is disturbed. Imagine a situation where a quantum event or outside force makes virtual particles turn into real particles. This stops them from disappearing like they usually would. This stability could cause energy to build up in areas of space where virtual particles usually don't last long. In this situation, energy that was supposed to last just a moment could be kept going and might keep increasing endlessly. The implications of such a runaway process are profound. In standard quantum electrodynamics, the effects of virtual particles are already observable in phenomena like the Lamb shift or the Casmir effect, where they contribute small but measurable corrections to the behavior of atoms and the forces between objects. Yet these effects are minuscule, precisely because the virtual particles vanish so quickly. If a mechanism were introduced, either by a novel interaction or a breakdown in our current understanding, that prevented their disappearance, the energy contained in the quantum vacuum could be released uncontrollably. In other words, what we perceive as nothingness might suddenly become a source of infinite, or at least extremely large, energy. Such an uncontrolled release of energy from the vacuum would have dramatic, far-reaching consequences. The fabric of space-time itself is influenced by energy density. According to general relativity, energy curves space-time, and an infinite or overwhelmingly large energy density could distort or even rip apart the continuum. The prospect of virtual particles going rogue, therefore, is not merely a theoretical curiosity. It poses an existential threat at the most fundamental level. If stabilized virtual particles were to create regions of anomalous high energy density, these regions might expand or interact in unforeseen ways, potentially triggering a chain reaction that could destabilize the entire cosmos. This hypothetical scenario forces us to confront a key tension at the heart of quantum field theory: the balance between the transient nature of quantum fluctuations and the immense potential energy they harbor. Under normal conditions, renormalization techniques allow physicists to tame the infinities that arise in quantum calculations, ensuring that predictions remain finite and well-behaved. However, if the delicate interplay that permits these mathematical cancellations were upset, if, for instance, a new physics mechanism were to stabilize virtual particles, then the very foundation of our understanding could be shaken. The notion of virtual particles going rogue challenges us to reconsider the stability of the vacuum and the nature of energy itself. While current experimental evidence and theoretical models suggest that such runaway behavior is highly unlikely, the possibility, however remote, underscores the latent instability hidden within the quantum fabric. It is a stark reminder that even the empty space we take for granted is a cauldron of potential energy held in check by precise quantum rules that, if ever broken, could unleash chaos on a cosmic scale. Quantum biology mutations, when life's code unravels. Quantum biology is a new area of study that looks at how quantum effects influence living systems. It explores how tiny particles and forces interact with chemicals and genetics, which may help us understand life's complexities and, in rare cases, lead to its breakdown. This idea suggests that tiny quantum events, usually found in the subatomic world, could impact the basic components of life. Quantum effects are believed to play a role in processes like photosynthesis and DNA duplication, which were previously thought to be explained only by classical physics. If these quantum processes don't work as planned, they could cause changes or problems in the coding of life, leading to serious effects. The notion that quantum mechanics might impact biology is not entirely new. Several studies have suggested that phenomena such as quantum tunneling could play a role in enzymatic reactions or in the transfer of electrons within cells. For example, in DNA, the possibility exists that quantum tunneling might enable protons to shift positions between base pairs, leading to tautomeric forms that can cause mismatches during replication. While such events are usually rare and well regulated by biological error correction mechanisms, a breakdown or alteration in these quantum processes could, in theory, lead to an increased mutation rate. This heightened mutational activity might trigger a cascade of genetic errors, potentially overwhelming the cellular repair systems and setting the stage for widespread genomic instability. Consider a scenario where a subtle quantum fluctuation in the DNA molecule, normally an innocuous event, becomes amplified due to environmental factors or underlying quantum instabilities. In such a case, the probability of proton tunneling might increase, leading to a surge in replication errors. Over time, these errors could accumulate, resulting in dramatic shifts in the genetic code. While mutations are a driving force of evolution, a sudden runaway rate of mutation could prove catastrophic, transforming beneficial adaptations into a chaotic scramble of genetic information. This process, akin to a mutation avalanche, might not only undermine the integrity of individual organisms, but also threaten the stability of entire ecosystems. The potential for quantum-induced mutations raises deeper questions about the fundamental nature of life. Life, as we understand it, depends on the stability of genetic information and the precise orchestration of countless biochemical reactions. If quantum effects can introduce unpredictability into these processes, then the very blueprint of life might be more fragile than we assume. In extreme cases, this fragility could manifest as a rapid, uncontrollable divergence from the norm, an event where life's carefully maintained code unravels, leading to either accelerated evolutionary change or widespread biological collapse. On the other hand, quantum effects might also help life show surprising strength, allowing it to adapt and use quantum changes to be more efficient or gain new abilities. Some experts suggest that nature may have developed ways to use quantum mechanics to improve processes like energy transfer in photosynthesis. However, this fragile balance between order and chance means that even a small mistake could upset everything. A small error in quantum data, if not fixed, could spread through a network of cells and lead to a change that affects normal biological activities. Ethics of quantum experimentation. Should we even try? As we reach the final frontier of our exploration into the most exotic and potentially dangerous quantum phenomena, we confront a question that is as much philosophical as it is scientific. Should we even push the boundaries of quantum experimentation when the stakes might be nothing less than the fabric of reality itself? This last part looks at the ethical issues related to studying quantum phenomena. While these studies provide amazing insights and technological breakthroughs, they also have the potential to cause harmful chain reactions. It makes us think about whether trying to gain information, no matter how good the intention, could put the universe we want to understand at risk. Quantum experimentation has already transformed our world, from the development of semiconductors and lasers to breakthroughs in quantum computing and cryptography. These advances have revolutionized technology, medicine, and communication, offering tremendous benefits to humanity. Yet, as our experimental techniques delve deeper into realms where quantum fluctuations could, in theory, trigger processes like vacuum decay, micro black hole formation, or uncontrolled phase transitions, we must pause to ask, what are the ethical limits of scientific inquiry? The first ethical consideration is the inherent unpredictability of quantum phenomena. In classical experiments, even when risks are involved, outcomes can often be forecast with a reasonable degree of certainty. In the quantum realm, however, the probabilistic nature of events means that even well-controlled experiments might yield unexpected and potentially disastrous results. For instance, while theoretical models suggest that the vacuum in which we exist is metastable only over unimaginably long timescales, the possibility remains that an experiment could inadvertently lower the energy barrier between our false vacuum and a true lower energy state. In such a scenario, a minuscule quantum fluctuation might initiate a bubble of true vacuum, expanding at the speed of light and rewriting the laws of physics in its wake. Though the probability of such an event is considered extremely low, the catastrophic implications force us to weigh the benefits of discovery against the existential risks. Another key issue is the balance between scientific curiosity and responsibility. The pursuit of knowledge has always been a hallmark of human progress, driving innovation and leading to profound insights about our universe. However, with great power comes great responsibility. Scientists and policymakers must consider whether the potential rewards justify the risks. Are there certain experiments that cross a moral threshold, where the possibility of unleashing uncontrollable, universe-altering phenomena outweighs the potential benefits of new knowledge? For example, particle accelerators and high-energy physics experiments are designed with extensive safety protocols and peer-reviewed risk assessments. Yet, as we push into realms where quantum mechanics and general relativity converge, domains where our current understanding is incomplete, there is a risk that unknown variables might produce outcomes far beyond our control. In this context, the ethical mandate becomes one of caution, to ensure that the drive for discovery does not compromise the long-term stability of our cosmos. We face a philosophical and scientific dilemma as we approach the last frontier of our investigation into the most exotic and potentially harmful quantum phenomena. Should we even attempt to push the limits of quantum experimentation when the stakes could be as high as the very fabric of reality? In this last section, we explore the moral considerations that arise when we attempt to understand quantum phenomena, which, although providing new knowledge and exciting technical developments, also pose the danger of setting off devastating chain reactions. It makes us wonder if, no matter how good our intentions are, we might put the universe we are trying to understand in jeopardy in our quest for understanding. The discussion of ethical boundaries in quantum experimentation must also address the issue of informed consent on a cosmic scale. Unlike medical research, where the subjects are individuals who can provide consent, experiments that touch upon the fundamental stability of the universe affect all of humanity, and perhaps even the cosmos as a whole. How can society agree to a course of action when the risks, though remote, could potentially impact every facet of existence? This dilemma forces us to engage in a broader, more inclusive dialogue about the kind of future we wish to create, one that weighs the thirst for knowledge against the imperative to safeguard the delicate equilibrium of the universe. Coming to terms with our own limitations is the last philosophical obstacle. Understanding, manipulating, and harnessing nature for human advantage is the foundation of the scientific method. However, the paradoxes and uncertainties of quantum mechanics serve as a reminder that there may be parts of reality that are actually beyond our ability to understand or control. Faced with these constraints, we need to consider if our desire to dominate the quantum realm is a sign of arrogance, a careless expansion into uncontrollable regions with potentially catastrophic outcomes. The moral obligation, then, is not only to increase our understanding of the world, but to do it with modesty, care, and a deep reverence for its complexity and fragility. Quantum futures, prospects for safety, control, and a stable cosmos. The scary and amazing possibilities of quantum effects can seem daunting, but scientists are not giving up on finding order in the universe. Researchers worldwide are working hard to understand, manage, and reduce these risks. As we learn more about quantum mechanics, we also improve our ability to create tools and methods that can help maintain the stability of our world, even as we explore new areas of quantum science. One major focus is the rigorous implementation of safety protocols in high-energy experiments. Facilities like the Large Hadron Collider, LHC, are not only at the cutting edge of particle physics, but are also equipped with extensive risk assessments and fail-safe mechanisms. These protocols are based on decades of theoretical research and experimental validation. By constantly refining our models of quantum behavior, such as the mechanisms behind vacuum decay or micro-black hole formation, physicists can set strict parameters on experimental conditions. Such measures ensure that the probabilities of triggering dangerous quantum events remain astronomically low. This continuous feedback between theory and experiment is critical to preventing any unintended chain reactions that might threaten cosmic stability. Outside the lab, researchers are looking for new ways to track and control possible quantum problems. One hopeful idea is to create worldwide quantum tracking networks. Scientists plan to place special monitors in key areas worldwide to spot any strange changes in the quantum vacuum or other early warning signs of instability. These networks could act like an early warning system, similar to how we track earthquakes, by alerting us to any unusual changes in the behavior of basic fields or particles. Having real-time data would enhance our models and help us create emergency plans if a quantum oddity is found. In addition to monitoring, significant research is being directed toward advanced error correction techniques in quantum computing and communication systems. As quantum technologies become more integrated into critical infrastructure, ranging from secure communication networks to financial systems, it is imperative that we develop robust methods to detect and correct errors that could otherwise cascade into larger failures. Fault-tolerant quantum computing protocols, which employ redundant qubits and sophisticated error-correcting codes, are a vital part of this effort. By ensuring that quantum systems remain coherent and free from error propagation, we can mitigate the risk of copying chaos or other deleterious effects that might arise from uncontrolled quantum events. A promising area for protecting our future with quantum technology is the study of quantum shielding. This idea focuses on creating materials or areas that can reduce or soak up harmful quantum changes. Even though it's still new, research in metamaterials and made quantum systems shows promise for creating a barrier, both in theory and in practice, to separate safe quantum activity from harmful events. For example, if we could change energy levels in a specific area or influence virtual particles, we might be able to reduce fluctuations before they become a serious problem. These new ideas might someday create a quantum firewall that keeps our larger physical world safe from the natural unpredictability of the quantum world. Working together internationally and creating worldwide rules are important for a safe future in quantum technology. High-energy experiments and quantum technologies can affect everyone, so it's important for scientists, states, and foreign organizations to collaborate. They should share information, establish safety guidelines, and work together to address any new threats. Just like international agreements manage nuclear weapons and space travel, we need similar rules for quantum research. These rules can help make sure that scientific growth doesn't compromise global security. Talking openly, being clear about risks, and sharing good methods are important to stop any project or technology from accidentally causing problems in the universe. The idea of using quantum effects for helpful purposes still brings hope. Quantum computing can greatly improve how we solve difficult problems, such as understanding climate change and finding new medicines. Quantum communication could lead to very secure encryption, protecting private information worldwide. In these situations, knowing and managing quantum effects is important not just to avoid problems, but also to open up new possibilities for technological advancements. By being careful and open to new ideas, people can keep exploring the quantum world while also staying safe from big risks. Philosophical and cultural implications: how quantum dangers shape our worldview. A complete change in how we understand what is real. For many years, people saw the world as a machine that worked like a clock, following fixed rules. This view gave them comfort and a sense of control. In comparison, quantum physics says that uncertainty, chance, and probability are basic parts of our world. This change from believing in fixed outcomes to considering probabilities has made many thinkers wonder if the reality we experience is set in stone, or just one possible result, shaped by how we observe and interact with the world. One obvious logical result is the question of whether things can be permanent. If even empty space can change and create new worlds or cause disasters like vacuum decay, then the security we think we have might just be an illusion. This makes us think, what does it mean for something to last forever? Is our universe just a temporary phase in a changing quantum world? These questions can challenge our most basic views about time, existence, and truth. These ideas resonate not only in the halls of academia, but also in popular culture. Science fiction has long explored the notion of a fragile reality. Stories of universes collapsing, time loops, and alternate dimensions abound in literature and film. Works like Interstellar, The Matrix, and countless novels have drawn on quantum theory to imagine futures where reality can be hacked, rewritten, or even reset entirely. These cultural narratives serve as both warnings and inspirations, shaping public perceptions of science and influencing how we think about the future. They underscore a growing collective awareness that the boundaries between science and philosophy are blurring, and that the most abstract ideas of quantum physics may have very tangible consequences for our world. These questions are important not just for fun, but also for social reasons. If we believe that the quantum world shows the universe is unstable, or that our actions could accidentally cause big disasters, then scientists and lawmakers have a huge duty. How do we satisfy our strong desire to learn and grow while avoiding dangers that could threaten our existence? This ethical problem is made more complicated because quantum experiments and high-energy physics study impact not just one country or age, but the future of all people. As a result, the conversation about the ethical boundaries of scientific research has become more important, and it needs to involve not just scientists, but also thinkers, ethicists, and the general public. Quantum doubt affects how we think about free will and whether everything is predetermined. In a world where results are based on chances, the idea of a set fate doesn't make sense. Some see this as a chance for more freedom, believing that the future isn't set in stone, but full of options that our choices can influence. Others, however, see this doubt as a source of existential worry, a warning that the security of the world is an ever-present gamble. The contrast between freedom and fear is a common topic in modern thought, which is now being brought back to life by new developments in quantum theory. These ideas have a significant cultural effect. In classes, meetings, and at dinner tables, people often talk about the idea that the world might someday glitch or break down. This topic makes them feel both curious and worried. It encourages us to rethink our position in the universe and to consider that the rules of nature, which we once believed could never change, might actually be able to change in significant ways. Quantum mechanics has changed from a small part of physics into something important in our culture. It helps us think about everything from what reality is to where humanity is headed. The quantum world is both a marvel and a nightmare, a realm where the fundamental rules of existence can bend, twist, or shatter entirely. While scientists continue to unravel its mysteries, one question remains: will understanding quantum mechanics save us or doom us? If you found this deep dive into the dangers of quantum instability as fascinating or terrifying as we did, don't forget to like this video, subscribe for more mind-blowing content, and hit the notification bell so you never miss a new exploration into the mysteries of the universe. And of course, share your thoughts in the comments. Do you think quantum mechanics is a key to ultimate knowledge or the ticking time bomb of reality itself? Let's talk about it.